Welcome back to The Explainer. Today we're tackling a highly practical, real-world scenario that perfectly bridges the gap between physical actions and digital control. We're going to be automating a physical sanitization process using PLC ladder logic. Imagine a secure facility door, or maybe a clean room entrance. We want to ensure that door is sanitized automatically, keeping things completely hygienic, but without requiring a human to just stand there with a spray bottle all day.
Okay, let's dive into this. How do we actually automate sanitization without literally spraying money down the drain? Think about the physical problem for a second. If you trigger a sanitization nozzle every single time the door handle is touched, or every time someone badges in, you're going to run out of sanitization fluid in a matter of hours. It's wildly inefficient. We need the system to be a lot smarter than just a simple one-to-one reaction. We need to trigger the nozzle efficiently, based on a very specific, measured threshold of use. To solve this efficiency problem, we have to establish strict physical rules for our system before we even think about writing any digital logic. Step 1. The door's unlock button must be pressed exactly 4 times. Not 1, not 2, but 4 complete uses of that door. Step 2. Only after that 4th and final press is registered does the sanitizer run, and it runs for exactly 10 seconds. Sounds incredibly simple when you say it out loud, right? But translating that precise sequence, reliably counting those physical presses, and then timing a spray into a ladder diagram requires a really specific progression of logic blocks. To get there, we'll run through setting up PLC tags, latching and memory bits, the progression sequence, the 10-second timer, and finally, simulating the process. All right, Section 1, setting up PLC tags. Let's transition from staring at a physical door into the digital world of TI Portal. Before we draw a single rung of ladder logic, our controller absolutely needs to know what physical hardware it's talking to. So we map our physical components directly to our PLC tags. We've got our unlock button functioning as our system's input, then we have the sanitization nozzle functioning as our output, and we'll assign it the specific address of Q0.0. Grounding these abstract addresses right from the jump is absolutely crucial. This way, when our logic eventually tells Q0.0 to turn on, we know that literally means fluid is spraying out of the physical nozzle. Section 2, latching and memory bits. This is where we tackle the core concept of how the PLC actually remembers that a fleeting physical action has happened. A button interaction isn't just one magic event, It's a press and it's a release. The PLC has to distinctly register both of these states to count it as one complete interaction. We track the initial press by using a memory bit we'll call M0.0, tying it to a normally open contact in our logic. But the user isn't actually done until they let go of the button. So to ensure we capture the whole physical event, we track the release with the next memory bit, M0.1, utilizing a normally closed contact. And that brings us directly to latching. Basically, latching is a method using memory bits to store the data that an action occurred. Why do we need this? Well, because a push button is momentary. The second a user's finger leaves the button, the physical input signal drops right back to 0. To fix this, we use a parallel contact of the memory bit itself to keep the circuit energized even after the button is let go. Think of it like a relay race runner passing a baton. M0.0 stores that first press and latches itself on. When the button is later released, M0.0 passes the signal forward, just like that baton, to M0.1, which then latches the release state. The PLC now permanently remembers that cycle happened. Section 3, the progression. Now that we've got that intricate press and release cycle down, let's fast-track through how this sequence repeatedly cascades to hit our target of 4 total presses. If you've ever had to replace a broken physical counter on a machine, you'll appreciate how elegant doing this in software is. Look at the pattern here. We start at one use, utilizing M0.0 and M0.1. Once M0.1 is safely latched, it serves as the gateway authorizing the system to look for the next press. That leads us right into use number 2, capturing that press and release with M0.2 and M0.3. The exact same rigorous pattern repeats for the third use with M0.4 and M0.5. These memory bits are acting as hard sequential checkpoints. You literally cannot jump to use number 3 without fully passing checkpoints 1 and 2 first. Finally, we hit the finish line at use number 4. When the button gets pressed for that 4th time, memory bit M0.6 gets latched. M0.6 is our golden ticket. It's the trigger that tells the system all criteria are met. Prepare for sanitization. Section 4, the 10-second timer. We've meticulously counted the presses using our memory bit sequence, so let's guide the system to the climax of the logic, where that final press actually activates the hardware. 10 seconds.
That's the exact preset value we need for our sanitization spray to be effective. When that final memory bit M0.6 goes true, indicating the fourth press, it triggers a timer block. Specifically, we're using a TP or timer pulse operation. We set the preset value of this timer to 10 seconds. The massive advantage of using a timer pulse here is that once it gets that trigger from M0.6, it immediately turns our output on, our nozzle at Q0.0, and keeps it forced on for exactly 10 seconds, regardless of what the user does with the unlock button afterwards. They could press it 50 times, it doesn't matter. Once those 10 seconds elapse, Q0.0 shuts off, the nozzle stops spraying, and the area is perfectly sanitized.
Section 5. Simulating the process.
Okay, we've built an incredibly sound logical structure, but we never just assume code works on the first try, right? Let's prove it. To test our setup, we load our project tags into the simulation table within TIA Portal and turn on the monitoring function. As we manually toggle the unlock button input on and off, we can literally watch the sequence of M bits cascade exactly as planned. We watch M0.0 hand off to M0.1 all the way down the line, verifying our logic is holding strong. Most importantly, we're verifying that only upon the transition to M0.6 does the TP timer actually start. And this brilliantly illustrates our success. Right on that fourth press, bam, we see Q0.0 go high for exactly 10 seconds, proving our physical nozzle is finally firing.
We just successfully used memory bits and latching to perfectly capture a 4-step sequence. It's a fantastic exercise in understanding state retention. But let me leave you with a provocative thought for your next project. You've mastered 4 presses, so how would you program this for 100 presses? Think about it. Writing out 200 individual memory bits for presses and releases would be an absolute nightmare. Actually, scratch that. It would be almost impossible to maintain. So as you scale up, it might be time to start looking into dedicated counter instructions to optimize your logic. Keep exploring those advanced tools, keep experimenting with your ladder logic, and I'll catch you on the next explainer.